It's the third video in the inner product space. If V is an inner product space with respect to this inner product, if V is an inner product space with respect to this inner product, here inner product is given simply straight away like this. We may put some 1, 2 there to distinguish different inner products. If V is an inner product space, then for x, y, z in V and for any constants, any scalars in the field F, show the following statements. We are going to see simple results for every vector spaces. If it is a vector space, if it is an inner product space, then this inner product is going to satisfy few more conditions, few more results. The first one is inner product of x comma y plus z. This is equal to inner product of x comma y plus inner product of x comma z. See here, the inner product in the second component, the addition in the second component also can be splitted for the inner products. The second one is the constants in the second components. The constant in the first components can be taken out, we have seen, but constant in the second components comes like this: c bar inner product of x comma y. And the third one is inner product of x comma 0 or inner product of 0 comma x, all are 0. And the fourth one is inner product of x comma x is equal to 0 if and only if x is equal to 0. And the fifth one is so important. It's a so important one. If inner product of x comma y is equal to inner product of x comma z for all x in V, then y is equal to z. Let us show these 5 statements. Proof. What's the first one? Addition in the second component can be splitted. If it is an inner product, then addition in the second component can be splitted. And constants in the second component can be taken like this, c bar. And if one of the component is 0, answer is 0. If inner product is 0, then x must be 0. If x is 0, then the inner product must be 0. This is a statement. If this is 0, x 0. If x is 0, then this is 0. That is the meaning of if and only if. And one more thing is, if these two are equal for every x in the vector space V, then y and z must be same. The first one, let us prove the first one, inner product of x comma y plus z. We have seen that from the third condition, this is equal to inner product of y plus z comma x, the whole bar, right? From the third condition, we know this one. And we know that addition, it's an inner product, right? So addition the first component can be splitted. So this can be written as inner product of y comma x plus inner product of z comma x. The bar comes as usual. This bar can be splitted. So inner product of y comma x, the whole bar, plus inner product of z comma x, the whole bar. So this one is equal to inner product of x comma y, and this one is inner product of x comma z. Now let us prove the second one. This is first one is our second one, inner product of x comma c y. This is equal to inner product of cy comma x. If we change the components, we have to put the bar. This is the third condition, right? So now we can take the constants outside. From the first component, we can take the constants outside. That is the second condition, right? Now we have to put the whole bar as it is. So this is, and bar can be separated. Z bar, Z1, Z2 whole bar is equal to Z1 bar into Z2 bar, right? So this is equal to C bar times inner product of y comma x the whole bar. So this is equal to C bar times inner product of x comma y. So the second condition, the constant has been taken outside but bar has come. The second condition also, second thing also proved. Now we have to prove the third one. What's the third one? Inner product of x comma 0. This is equal to, we may write this as inner product of x comma 0 times some y. This is equal to 0 bar times x comma y, right? This is equal to 0 only. Similarly, inner product of 0 comma x. This is equal to, we may write this as 0 times some y comma x. This is equal to 0 times y comma x. So this is equal to 0 only. 0 times a number is 0 only. So this is equal to 0. And fourth condition, what we have to prove? Inner product of x comma x. If this is equal to 0, then we have to show that, x equal to 0. See, note, if x is not equal to 0, then inner product of x comma x is positive. This we have seen. This is the definition of inner product, right? But here it is given it is equal to 0. Okay, so x is not equal to 0. Also, for x is equal to 0, inner product of 0 comma 0, inner product of 0 comma 0 is equal to 0 only. So this implies 0. This implies x is equal to 0. Converse. If x is equal to 0, then this is also 0. Nothing to prove here, right? Unnecessarily we are proving this one. See, this is equal to 0. That means x cannot be non-zero. And if x is equal to 0, if we put x is equal to 0, we get 0. So this is equal to 0 implies x must be 0 only. And if x is equal to 0, we have to prove this one. That is also obvious from this one, from the above statement. Let us prove the fifth one, a so important one. So important one, the fifth one. What is the fifth one? If inner product of x comma y is equal to inner product of x comma z, if these two are equal for all x in the vector space V, then we have to show that y is equal to z. Now consider this one, inner product of x comma y minus z. this is equal to inner product of x comma y minus inner product of x comma z, right? Because it is y plus of minus z. The addition of the second component can be splitted. So we can write this as how x inner product of x comma y plus inner product of x comma minus z. That minus can be taken outside. Minus 1, the whole bar is minus 1 only. But these two are always equal. So this is equal to 0 for all x. For all x it is 0. So instead of x, even if you take y minus z, this has to be 0 only. But just now we have seen that if this one is 0, then y minus z is equal to 0. This implies y is equal to z. It's a simple proof but important results. So if this one is an inner product, then these 5 more conditions also hold for the inner products. Now we are going to define a new notion called norm, or length of a vector x. In R2, just take a point, a vector v is equal to x comma y. Then what is the distance? This distance is denoted as norm v is equal to square root of x square plus y square, right? This is the distance, square root of x square plus y square. So for every vector there is a distance from the origin. So similar notions is going to be called as norm v is going to be defined now. Definition. Norm of x. Definition. Let this be an inner product space. V is a vector space, is endowed with some inner product, is called inner product space. For x belongs to v, we define the norm or length of the vector x by norm x is equal to non-negative square root of inner product of x comma x. Note that inner product of x comma x is always positive for a non-zero vector. So if we take the square root, we will get a positive number only. So this is positive if x is non-zero, and this is equal to 0 if x is 0. If x is 0, this 0 comma 0, inner product of 0 comma 0 is 0, so the square root also is 0. Note that. Okay, we have seen a standard inner product, right? Fn, this is a standard inner product space, is the standard inner product space. So here what is the norm? If we take x, what is x? If we take x is equal to a1 etc. an in Fn, what is the norm x? Norm x is equal to square root of inner product of x comma x. What is inner product in the standard, this one? What is inner product? Summation ai bar. I runs from 1 to n. Instead of square root, we put whole power n by 2. So what is this one? So the norm x is equal to summation mod ai square whole power 1 by 2. Just now we have seen this one, right? Square root of x square plus y square. So this one. This is the Euclidean distance. That's why it's called standard inner product. This inner product derives the Euclidean distance, is the Euclidean norm, is called the Euclidean norm. Now let us prove few more conditions, results for the norm, for the inner products and for the norm. Now let us see few more results. These two are so important results. Let this be an inner product space. Then for all xy in B and for every scalars in the field F, show the following. Norm Cx is equal to modulus of C into norm x, and norm x is equal to 0 only if x is equal to 0, and modulus of inner product of x comma y is always less than or equal to norm x into norm y, and norm x plus y is less than or equal to norm x plus norm y. This result is called Cauchy-Sparse inequality. Cauchy-Sparse inequality, and this result is called triangle inequality. Now let us prove all the statements. First one, norm Cx. Take the norm Cx square. Take norm Cx square so that the square root will go away, right? So we get Cx comma Cx, inner product of Cx comma Cx. Instead of this square root, we have put here square. So this C can be taken outside as it is. This C comes as C bar, right? So C bar is modulus of C square. This is norm x square. If you take a square root, positive square root on both sides, we get norm Cx is equal to modulus of C into norm x. So the first result is over. And now let us see the second one. What is that one? Norm x is equal to 0. This implies inner product of x comma x is equal to 0. This implies x is equal to 0. Similarly, if x is equal to 0, this implies inner product of x comma x is equal to 0. This implies norm x is equal to 0. Actually, if norm of any vector is 0, that vector must be a 0 vector, or otherwise that norm will be positive only. Now let us prove the third one. Cauchy-Sparse inequality is so important one, and by using the Cauchy-Sparse inequality, let us prove the triangle inequality. Now let us prove the Cauchy-Sparse inequality. What is the inequality? Modulus of inner product of x comma y is always less than or equal to norm x into norm y. Okay, let us prove it. Proof. If y is equal to 0, if the vector y is 0, then the inner product is 0, the left hand is 0, the right hand is also 0. So 0 is equal to 0, nothing to prove. Then nothing to prove. Because obvious, if y is equal to 0, left hand side is 0, right hand side also 0. So let y is non-zero. Let y be a non-zero vector. So we may take y as, so consider x minus cy. It is so a tricky proof actually. Consider x minus cy and norm of this square. Norm of anything is always non-negative, right? This can be written as inner product of x minus cy comma x minus cy. This can be written as inner product of x comma, just I am splitting the first component, so x comma x minus cy minus, I am taking c outside, minus c times inner product of y comma x minus cy. And from this one I am splitting the second component, so I am getting inner product of x comma x, and if I take the c outside, I get minus c bar, minus c bar inner product of x comma y, and from this one minus c inner product of y comma x, and minus of minus plus, so simply I get plus c times c bar inner product of y comma y. Just where c is a constant, where c is a scalar, please, c is a scalar. Now for the scalar I am going to choose this inequalities holds for every c, right? Every c. I am going to take c is equal to inner product of x comma y by inner product of y comma y. Actually it's a tricky proof. See, just I started from here. This inequality is true, everyone knows, and I am choosing cleverly we are choosing our c, so that the proof comes very trivially. I am choosing my c as like this one, and I am going to substitute this c here. Okay, substitute this c in this equation. This is the left hand side is 0 less than or equal to inner product of x comma x minus c bar. C bar means here I have the denominator is always a real number, so no need to put any bar. Here if you put any bar, it comes as inner product of y comma x. Here already x comma y, so we get mod inner product of x comma y the whole square only, because here if you put bar we get y comma x, here x comma y already here, so it's like z bar, so we get if you put bar here we get z bar, so that is mod z square by inner product of y comma y minus let me write here minus c. C is inner product of x comma y by this one is norm y square, right? Norm y square into inner product of y comma x plus c bar. C means x comma y, c bar means x comma y the whole bar. Okay, x comma y the whole bar is y comma x. C means x comma y by let us write norm y square. It is c. It is c. C bar means this one by norm y square or inner product of y comma y, and here we have one more y comma y, right? This one both will get cancels, and also see that the remaining this term, this one as well as this one, here we have minus sign, these two get cancels, so we get the inequality as 0 is less than or equal to inner product of x comma x minus modulus of inner product of x comma y the whole square by norm y square. It is norm x square, right? This is norm x square minus modulus of inner product of x comma y the whole square by norm y square. If you take if you multiple, actually y is a non-zero vector, so norm y is positive, so if you multiple on both sides by norm y square, we get here norm y square, right? Just I am multiplying on both sides, so we have got the inequality. It is a minus of this one. Take this one to the left side, so modulus of the product of x comma y the whole square is less than or equal to norm x square into norm y square. Take the square root on both sides, we get modulus of inner product of x comma y is less than or equal to norm x into norm y. This inequality is called Cauchy-Schwarz inequality. This inequality is called Cauchy-Schwarz inequality. Now let us prove the triangle inequality. The fourth one. What is the triangle inequality? Norm x plus y is less than or equal to norm x plus norm y. Let us prove it. What is norm x plus y? The whole square. This is equal to inner product of x plus y comma x plus y. This can be written as inner product of x comma x and inner product of plus inner product of y comma x plus inner product of x comma y plus inner product of y comma y. If we expand, we will get this one. This is equal to, the first one is norm x square, the last one is norm y square. What is this one? This is z. It is, this one can be written as inner product of x comma y, the whole bar, this one plus inner product of x comma y plus norm y square. It is z bar. So z bar is, in complex analysis we have studied what is z bar. This is equal to 2 times real part of z. This is equal to norm x square plus 2 times real part of inner product of x comma y plus norm y square. But real part is always smaller than the real part of z. See, real part of z is always less than or equal to mod z, right? So instead of this one, I am going to replace 2 times mod of this x comma y. Okay, plus norm y square. But see, from the Cauchy-Schwarz inequality, this one is less than or equal to norm x into norm y. The rest of the terms comes as it is. So what is this one? This can be written as norm x plus norm y, the whole square, right? So we have got that. What we have got, we have taken the left hand side as norm x plus y the whole square. The right hand side is this one. So we have arrived that norm x plus y the whole square is less than or equal to norm x plus norm y the whole square. So norm x plus y is less than or equal to norm x plus norm y. This is called the triangle inequality. We have used the Cauchy-Schwarz inequality to prove this one. This means that assume that this is x, this is y, this is x plus y, this x plus y, this one, this x plus y will be smaller than this distance plus this distance. This is x vector, means this is also x only. Always this one will be lesser than this one plus this one. So we get a triangle, right? So it's called the triangle inequality. This is the shortest one. Let us see other properties and norms and a few more Cauchy Gram-Schmidt process later in the next session, next video. Thank you.